So today I will cover on this NanoDCAL software, and firstly I will give you some brief presentation about the feature and characteristics of this NanoDCAL software, and after that I will demonstrate you live. And in the second session you can do the hands-on practice. So if we talk about this NanoDCAL software, so this NanoDCAL is very state-of-art general purpose first principle quantum transport package, which combine both density function theory and non-equilibrium green function theory. This software is written in MATLAB and C language. And this software is used in lot of publication papers and good journal. So you can find on the Google Scholar page where many of the paper published in many domains like spintronics, battery and energy storage device, insulator, topological insulator, photocurrent, molecular electronics domain, and it cover all the application. So it can focus on electronics property as well as spin transport properties like IV characteristics, including field effect, dielectric effect, spintronics application like collinear spin, non-collinear spin, spin orbit coupling, and it include all the common analysis tools like density of state, Phonon density of state, local density of state, projected local density of state, band structure, complex band structure, thermal transport tools, and Phonon tools. So this all feature will be there so that you can model the structure very easily. Here you can see these are the some publication papers that is published by using this NanoDCAL software. And you can see this is the device structure where we have the left electrode, right electrode, and center region. So not only the left and right electrode, you can also define the front electrode, back electrode, top electrode, gate electrode. So up to 6 probe device structure you can easily simulate from this NanoDCAL software. Now this NanoDCAL can also work on spintronics application apart from the semiconductor, material science, graphene, and other 1D and 2D material. So it can work on spintronics application for the next generation nanoelectronics and device configuration for the lower power consumption, higher density that will increase your device performance. So not only the spintronics application, you can also study battery, energy storage device, photocurrent calculation, spin movement, spin up, spin down calculation, nano ribbon, and different other kind of structure also you can simulate. You can also define the polarization like rho, theta, and phi in your structure throughout this spintronics application. You can also include the spin orbit interaction. You can also define the electric field application, magnetic field application. So these all type of simulation you can study from this NanoDCAL software. So this NanoDCAL can also work on photogalvanic spintronics application. Like you can design a multiple layer structure like monolayer, bilayer, tri-layer. So multiple layer structure. Here you can see this is the 3-layer structure where the graphene is sandwiched between 2 boron nitride. Where we have the different material. We have the left electrode, right electrode, and center region. So not only the left and right, you can also define the anode, cathode, front and back electrode, bottom and top electrode, gate also you can define, and you can also define the magnetic moment at different edge atoms. You can see this is the stagger potential that is produced by 2 boron nitride. And in this structure, we have defined the collinear spin so that we can get the result of spin up and spin down. And based on the spintronics application, what will be the band gap in your seed? That type of study you can analyze. So apart from this, NanoDCAL can also work on semiconductor device application, molecular based device structure simulation. So here you can see this is the device structure where the gate voltage is applied. And based on the gate voltage, you can find the IDBD characteristics, IGBG characteristics, transmission spectrum, and other properties like photocurrent, conductance, thermoelectric current, and many more device property you can study from this NanoDCAL software. You can see this is the publication papers that is published by using this NanoDCAL software. So this is the two-probe device structure, molecular-based device structure. In the center region, you can see we have the molecule, and in the left and right, you can see we have the graphene sheet. And for this device structure here, you can see we have simulated the transmission spectrum with respect to Fermi energy. So semiconductor device application, you can also study from this NanoDCAL software. So this NanoDCAL can also work on mesoscopic electronic transport in twisted bilayer graphene structure. Like if you have a planar sheet and that planar sheet you want to twist at any particular angle, particular radius, and you want to define as well. So you can also perform that electron transport by twisting the graphene sheet. Here you can see this is the twisted graphene sheet. We have the circular region, left region, and right region. So we have an angle position where you can select what position, left and right you want to select. Accordingly, you can find the EK diagram, transmission coefficient, and other property from different variation. You can also find the Eigen state, potential distribution, and many more properties by rotating and twisting the sheet. So you can also work on 4-terminal devices, 2-terminal devices, nano ribbon, nano wire, grain boundary structure, surface structure, crystal structure, molecular-based device structure. Like here you can see, this is the 4-probe device structure where we have the left electrode, right electrode, top electrode, and bottom electrode. And based on your device structure, you can find the IDBD characteristics, IGBG characteristics, band structure, conductance, thermoelectric current, CA coefficient. So many more device property you can calculate. Similarly, you can rotate a tube at any angle, at any particular radius, and based on the rotation, how much will be the defect in your sheet, a tube that you can study. If we talk about why this Nano Academy technology software is world class, so basically they are a team of nanoelectronics, physics, applied computing physicists, and expert developing atomistic and quantum simulation tool for the advanced application. So just a few words about the features and characteristics of our tools. So our tool include pretty unique features, atomistic and quantum transport features. Also, we can predict the material properties and the electronics and physics property of material that will reduce the project time frame and accelerate the time to market, which is very important for the research and development. We also offer the fast converging tools with the advanced algorithm, and we also offer the efficient parallelism and a scalable design in our course. So plenty of tutorials and extensive documentation are there so that user can get started quickly. And to enhance the user experience, we also offer the user-friendly graphical user interface, such as Python API in the new version. And we also enable the integration of third-party solution for plotting and displaying the curve. Just for rest, notably, we offer a free 1-year service for the advanced technical support of our tools. So you can see these are the product NanoDCAL Rescue QT CAD that is developed by this Nano Academy technology. So if we talk about this NanoDCAL software, so this NanoDCAL is for the material as well as device simulation based on the density function theory and non-equilibrium green function theory. Also, they have developed this rescue software that is dedicated for the material simulation. So based on the density function theory and density function perturbation theory, you can simulate any material. Also, they have developed this QTCAD software. So basically, this QTCAD software is a TCAD software based on the FEM method. So you can simulate the spin cubic devices in the semiconductor. So this is the brief idea about this NanoDCAL software. Now I would like to demonstrate you live and show you some features about this NanoDCAL software. So you can see this is my C drive, this is my device studio, and here you can see this is the bin folder. Also, we have the new version of this device studio that is under development. So this is the bin folder, and here you can see this is my device studio application file. So I need to open this file. And here I would like to start from the scratch. So create a new project, select this OK. And here I would like to enter the project name. You can select the location where you want to save this project, and then you can click on the save option. So basically, this is the device studio graphical user interface of the NanoDCAL and rescue software. So this device studio will help you to build your structure. You can build your crystal structure, molecule structure, device structure, and manipulate these properties. This is my project explorer where the input and output file will be shown. This is my property explorer where the property of whole structure or individual atom you can see. And this is my job manager. So yesterday I have already covered the rescue software. So this rescue software I have already covered. So today I will cover this NanoDCAL software. So first I will take some material and then I would like to simulate that material based on the NanoDCAL software. After material simulation, I will also take some device and simulate their properties. So this is my menu bar where we have this file option. This is for creating a new project. You can open your existing project. You can save the project. And here you can see this is the new option. So if you want to create any device structure, you can see this is the device builder that will help you to build your device structure. Like you can select any type of structure like left right device structure, left center right device structure, bottom and top device structure, bottom center and top device structure, front and back device structure, front center and back device structure. So up to 6 probe device structure you can easily simulate from this NanoDCAL software. Here you can see this is the left center right structure. Whenever you select, here you can see you need to import some material for the left electrode, center region, and right electrode. So before going to the device builder, first we need to import some material so that we can define their left electrode, center region, and right electrode. So you can see this is the basic information that we need to enter. And here you can see this is for the advanced application. Here you can import the material. Then you can define the surface vector. For the left electrode, you need to import the center material. Then also you need to define the surface vector for the center region. So I would like to take some material from our existing database. So you can see this is the file option. This is the import option. And this is the import local. So you can see this is my material database where we have the 0D material, 1D material, 2D material, 3D material, and some organic material. So I would like to select this 3D material, select this layer material, and I would like to import this MOS2. You can see this is the MOS2 layered material. So you can see this is my MOS2 that I have imported from our local database. So here you can see this is the properties of this structure. Like we have the total number of atoms is 9. This is the vector value, vector A, vector B, vector C, and this is the total area of this lattice. So if you want to select only single layer MOS2, then we need to delete these atoms and these atoms. So you can see the atom has been selected, and now you can click on this delete atom, so that this atom will be deleted, and we have single layer MOS2. Now I would like to select this delete atom, and you can see this is my single layer MOS2. If you want to simulate this structure with the help of NanoDCAL software, you need to select this simulator, NanoDCAL, and in the NanoDCAL you can see multiple options are there. You can see this is the virtual crystal approximation. So if you want to include any doping, you can see this is the virtual crystal approximation. Here you can see this is the mixture vacancy where we have the element, like we have the molybdenum and this sulfur, and their basic function, like this is the pseudo potential database, LDA double zeta polarized. You can see this is the doping. We have the p-type doping and we have the n-type doping. You can select any doping, then you can define their value. You can see this is the p-type doping and this is the n-type doping. So p-type doping you can define from this mixture vacancy. And if you want to mix any atoms in this structure, so we have this mixer atom. So if you want to mix any atoms in this structure, so you need to select this add option, so that new element will be added. You can see this default carbon atom has been selected. So if you want to change this carbon, you can double click, then the periodic table will be open. And from this periodic table, you can select any element. Like you can see, this silicon has been selected, and you need to click on this OK. So once you change the element, you also need to define the composition. Like you can see 0.75% is molybdenum and sulfur, and this 0.25% is silicon. If you want to add more atoms, you need to select, and also you need to define their composition. But by adding all the composition value should be 1. So basically it depend upon you what the composition value you want to define, you can select. So once you define, then you can click on this generate file so that the input and output file will be generated. Here you can see, I would like to select this n-type doping and click on this generate file. So it will take a little bit time to generate the input and output file. Now here you can see, this is the virtual crystal approximation input file, and here you can see this is the doping output file. You can see we have defined the n-type doping and their value is 1.001. So similarly, you can also include any doping and then you can enhance their various properties from this analysis option. And if you want to define some DFT parameter, so here you can see we have the cell consistent field calculation so that you can define your DFT parameter. And if you want to optimize any structure, so for optimization, we have this relax option. You can see these are the relaxation method. Like we have this molecular dynamic and we have the conjugate gradient. And in the rescue, we have the steeped descent, conjugate gradient. So any method you can select and then you can generate their input file. So suppose if you want to define this EMD, you need to generate this file. Here you can see the input file has been generated. So this is the relax.input file. You can see this is the relax parameter. So once you simulate this structure, then it will generate an output file. So optimized structure, it will generate. Like here you can see, I am going to simulate this relax.input file. And now this relax.input file is in the running condition. So when this input file will be completed, then it will generate an output file. So this is for the optimization. And if you want to define some DFT parameter, so you can select this SCF calculation. And here you can define your parameter. Like you can define the electron temperature. Any value you can change. Like you can see this is the 100 electron temperature. You can also change the cutoff energy in the unit of RT, read-over, and electron volt. You can see this is the exchange correlation function LDA and GGA. So in NanoDCAL we have the LDA, GGA, and in the rescue we have LDA, GGA, meta GGA, and a hybrid function. You can see this is the K-point sampling. This is the iteration control. You can see this is the tolerance where we have the density matrix and Hamiltonian matrix. You can also select this total energy, then you can define their value. You can see this is the basis set, like this is the arrangement of this structure by element or by atom. This is our molybdenum and sulfur atoms and their pseudo potential file. You can also change PBE double zeta polarized, and a user defined database is also there. This is the LDA plus U, that is basically for the Howard atoms, so that you can define their SPDF combination. And this is for the spintronics application. Like you can see, this is the no spin, this is the collinear spin, and then you can define their spin polarization rho value. So you can also change the value of rho from -1 to 1. If we talk about this general spin, so that you can define the spin polarization rho, theta, and phi. You can also enable this spin orbital interaction. So here you can see I have generated this relax.input file, and this input file is in the running condition. So I can copy this structure and I can generate their SCF.input file. So you can see this is the SCF calculation for this crystal, and here I would like to take collinear spin. So once you define all the parameter, then you can click on this generate file, so that the input file will be generated. Now you can see this is our SCF.input file. And if we talk about the script, so you can see this is the script for this MOS2. You can see this is the SCF calculation. This is our basic setting parameter, electron temperature, cutoff energy, exchange correlation function LDA, K point sampling, collinear spin is included, iteration control parameter, basis set. You can see atom, these are the orbital, and here you can see this is the XYZ coordinate point. And also you can see this is the spin polarization rho value. So this is the script. So there is no need to write any script for any structure. Simply you can define your parameter and click on generate file. So this software will automatically generate their input file. And if we talk about the analysis, so what the property you want to analysis from this structure, you can select this analysis. You can see these are the material property. So for any material, you can analysis these properties. Like you can analysis the density of state, effective potential, total energy, band structure, charge, Hessian matrix, Phonon band structure, electron density, potential, transmission channel, Eigen state, full band structure, effective mass, complex band structure. ZT is basically for the thermoelectric application, Phonon full band structure, Phonon density of state, Phonon transmission channel, and modulus. So any parameter you can select, you can click on this generate file. Suppose if you want to select this density of state, here you can see this density of state has been generated, and here you can see we need to define some key point sampling. Also you can see this is the number of energy point, this is the energy range, and this is the projection. Projection in this sense you can see this is the default none option, this is the atom orbital, and this is the ELN. So whenever you select the atom and orbital, then a density of state will be plotted with atom and orbital wise. And if you selected this ELL, then a density of state will be plotted with orbital with angular momentum. So these are the various projection. Here you can define some K-point sampling. Like you can see, I would like to select a default parameter 333. You can see this is the band structure and this is the symmetry K point. Here you can see, if you want to show the path, so this is the Brillouin zone path of this EMOS2 structure. You can see symmetry K point and their value. You can also add any other symmetry point from this new option. You can also delete any symmetry point. Then select preview. Then you can select this supply. So basically this is the band structure. And before calculating this Phonon band structure and ZT, first we need to calculate the Hessian matrix. Here you can see, first we need to calculate the Hessian matrix so that we can analyze the Phonon band structure and thermoelectric application. Now you can see this is the electron density, and in the electron density we can see this is the charge density, total electron density, row density, bond density. So multiple density are available. So as per your need, you can generate, select the file in, select the density and generate their input file. You can see this is the potential, and in the potential you can see this is the effective potential, Harty potential, and exchange correlation potential, and neutral atom. So these are the different potential. You can see this is the transmission channel. So if you want to analyze the transmission channel, you need to define the parameter. Here you can see this is the Eigen state. So once you define the parameter, then you can select this generate file. Now I would like to select this Hessian and this Phonon band structure. You can see this is the Hessian matrix, delta, their order, and the moving atoms. You can see this is the Phonon band structure. So multiple file you can select and then select this generate file. Here you can see our relax.input file has been completed, and you can see optimized input file has been generated. Here you can see this is the optimized parameter. You can see this is the vector value, vector v1, v2, v3, and this is the optimized coordinate point. So if you want to show the optimized structure, so you need to import this input file. So you can see this is my location. So if you want to import this file, you can select this import, import local. You can go to your project location. You can see this is my project location. Here you can see this is my MOS2 folder, NanoDCAL crystal, and here you can see this is the atom relax.xyz file. So this file I would like to select, and you can select this open. Now you can see this is our optimized structure. You can see this is our current structure and this is our optimized structure. You can see the variation in the vector value. vector A, vector B, vector C, total area of this lattice. And if you select this one, you can see these are the changes. So there are some minor changes in this structure. And then you can do the simulation for this optimized structure. And if you want to run this input file, scf.input file, you can run. Similarly, you can run all this analysis input file. So you can see this is the density of state. I would like to select this run option. And here you can select this run to run this job. So you can see in the queue condition, I would like to run all this input file. So once the simulation completed, their output file will be generated. Now you can see in the queue condition, I have run all this input file. Like when this input file will be completed, then this input file will start automatically. So in the queue condition, you can run multiple input file. And once the simulation completed, then you will get the output file. You can see this is the relax background simulation. You can see we have defined the MD method, molecular dynamic, and here you can see this is the structural relaxation, step 0, step first. You can see maximum atomic force for the step first, step 0, step 2. So it has taken 25 step. And at the 25 step, you can see this is the maximum atomic force. Now you can see our scf.input file has been completed. Density of state completed, band structure completed, electron density completed, potential completed, and now this transmission channel is running. Here you can see we have get the output file. So you can see this is the density of state.xml file. If you want to open this output file, you need to select, right click, select the show view. You can see this is the density of state for this MOS2 with respect to energy. And here you can see this is for the spin up. And also you can see this is the spin up, this is the spin down, and this is the both spin up and spin down. So if you want to export this raw data, here you can see this is the export option. You can select this file format like PNG, JPG, BMP, PDF, TIFF format, EPS format, and text format. So any format you can select, like you can see this is the text format. You can choose the location, select this save option. Now you can see the file has been exported. So you can see this is the density of strain for the spin down and this for the spin up. Now you can see this is the band structure. So this is the band structure for the CMOS2. You can see from 0 to 10, this is the conduction band, and from 0 to -10, this is the valence band. And here you can see this is the Fermi energy. So this is for basically spin up. Here you can see this is for the spin down. And you can see this is for the spin up and spin down. You can see this is the Fermi energy, and our Fermi energy is located at the middle of the band gap. You can also select different position like top of the valence band. Also you can see bottom of the conduction band. And this conduction, so this is the bottom of the conduction band, and this band structure are in the unit of energy, that is electron volt. But when you import this file into MATLAB, then you will get the energy in the unit of RT. So this is the band structure. Here you can see this is the total electron density. So this is the total electron density 3D view. You can see this is the 2D view. Average along x-axis, y-axis, and z-axis. You can see this is the planar display. This is the stereoscopic display. Along z-axis, y-axis, and x-axis. So this is the 2D view, and here you can see this is the 1D view. Average along xy plane, yz plane, and xz plane. So this is the total electron density. You can see this is the effective potential. You can see this is the ICO surface. So this blue area is a ICO surface. You can also increase or decrease the value from this arrow option. You can see this is the 3D view. This is the 2D view along x-axis, y-axis, and z-axis. You can see this is the 1D view. XY plane, YZ plane, and XZ plane. This is the transmission channel. You can see this is the transmission channel with respect to energy. Here you can see we have the channel number. This is the spin type where we have the spin up, spin down, and this is the both spin up and spin down. So both the data are overlapping, you can see. And this is the total transmission channel. Here you can see this is the Eigen state. So this is the Eigen state. So this is the 3D view. Here you can see this is the band value. This is the spin. This is the 2D view along x-axis, y-axis, and z-axis. And you can see this is the 1D view. So various material property you can simulate from this nanodical. And here you can see this is the Phonon Band structure. So this is the Phonon Band structure for this EMOS2. You can see this is the symmetry K point, and here we have the phonon energy. So if you want to calculate the thermoelectric application, so first you can select this open containing folder so that you can find the location of the project. And for the thermoelectric application, we need to import this NanoDCAL object file. So this NanoDCAL object .mat file we need to import while calculating the ZT. You can see this is the simulator NanoDCAL. Here we have this analysis. You can see this is the ZT, and in this primitive cell we need to import the NanoDCAL object.mat file. So we can browse our file. You can see this object.mat file we need to import. Now you can see the file has been imported. Then you can define the K point sampling, Q point sampling, energy range, temperature range. Then you can choose the direction. So once you define the parameter, select this generate file. Then it will generate ZT.input file. And this file you need to run so that you can get the thermoelectric properties. Now you can see this ZT.input file is in the running condition. Here you can see this is the ZT input file. Starting the calculation, you can see this is the calculation of the thermoelectric properties. Now the simulation is running. So if we talk about the semiconductor heterojunction, so if you want to create a heterojunction of the semiconductor, so first we need to import the semiconductor material. You can see I would like to import the semiconductor from our database. You can see this is our semiconductor material. And here I would like to import the gallium arsenide. You can see this is the gallium arsenide semiconductor. Again, I would like to import one more semiconductor. And which is aluminum arsenide. So you can see this is our gallium arsenide and this is our aluminum arsenide. So for creating the heterojunction, first we need to convert this structure into supercell. So you can see this is our gallium arsenide, and if you want to create a supercell, so you can select this build option, select this redefine crystal. So you can redefine your crystal in any direction, either direction A, direction B, and direction C. So you can see, I would like to make a supercell 2 times in the A direction, 2 times in the B direction, and 4 times in the C direction. Select this preview. You can see this is our supercell of this gallium arsenide. So once you define, then you can select this build option. So in the same way, you can select this aluminum arsenide and you can make a supercell. Select this build option, select this redefine crystal. Here again, I would like to redefine 2 times in the A direction, 2 times in the B direction, and 4 times in the C direction. Select this preview. You can see this is the supercell of this aluminum arsenide. Then you can select this build option. So now this is our gallium arsenide supercell and this is our aluminum arsenide supercell. So if you want to create a heterojunction, you need to select this build option, select this interface builder. So this is the interface builder where we need to import the material for the structure A and structure B. You can see I would like to import this gallium arsenide supercell structure, and again I would like to import this aluminum arsenide supercell structure. Also you can define the constant value. You can also define the rotation. You can also choose the strain value. Like you can see, this is the strain surface, strain first surface, second surface, and both surface. So once you select this parameter, select this match option. And now you can see, this is the graph between number of atom versus mean absolute strain in percentage. At that point, you can see, we have the atom number, we have the angle, we have the rotation, we have the mismatching, area, and strain value u, v, and theta. If you want to change any point, you can see the value are changed. So once you select this match option, select this preview, and you can see this is our semiconductor heterojunction between the gallium arsenide and aluminum arsenide. You can also change the number of atom. So in the same way, you can create any heterojunction for any structure. Like if you want to create a 2D heterostructure, like you can see this is the semiconductor heterojunction. And if you want to create a 2D heterostructure, then you need to import 2D material. So I would like to import 2D material. You can see this is our 2D material. And from here, I would like to select this graphene. Again, I would like to select hexagonal boron nitride. Again, you can create a supercell of both graphene and hexagonal boron nitride, and then you can go to the interface builder to create a 2D heterostructure. Like you can see, this is the graphene. I would like to select this build option, redefine the crystal, and here you can redefine in any direction. Like you can see, I would like to define 56 in the A and 56 times in the B direction. Now you can see, this is the supercell of this graphene structure. Then you can preview, then you can click on this build option. Again, you can select this hexagonal boron nitride, select this build option, select this redefine crystal. Like here you can see, I would like to define 56 times in the A direction, 56 times in the B direction. Select this preview, and you can see this is my hexagonal boron nitride supercell. Select this preview, select this build option. So if you want to create a heterostructure, you need to select this build option, select this interface filter. Here you need to import the material. Like you can see, this is our graphene supercell structure, and this is our hexagonal boron nitride supercell structure. Select this match, select this preview. You can see. So in that way, you can create a supercell interface between any structure. And if you want to rotate any structure, you can see, if you want to rotate this structure, you can select, then select this rotation option. Here you can see, this is the rotation. We need to rotate in any direction, like either screen vector, XYZ axis, or ABC vector. Then you can define the angle value here, and then select the direction. Like you can see, I would like to define 1.15. Select the direction. So in any direction, you can rotate. Now you can see.
Excuse me, sir.
Yes, sir.
Can you calculate the surface energy of the that heterojunction?
Surface energy.
Yes.
Yes, sir. Energy we can calculate. So you can see. So once you create the heterostructure of any atom, any structure, then you can select this simulator. First, you can generate the input file. You can define some DFT parameter, and then you can go to the analysis. So in the analysis, you can select this total energy, so that you can get multiple energy points like kinetic energy, surface energy, VNL energy. So multiple energy you can get. So you can see it will take some time because there are lot of number of atoms. So energy you can calculate.
Thank you, sir.
And if you want to design a device structure, here you can see our thermoelectric input file has been completed and their output file has been generated. So this is the thermoelectric properties. Here you can see this is the conductance with respect to temperature. Also you can see this is the temperature conductance with respect to chemical potential energy. In the plot type, you can see this is the conductance, this is the Seebeck coefficient. You can see this is the Seebeck coefficient, with respect to chemical potential energy. Also, you can see with respect to temperature. So this is the Seebeck coefficient, and here you can see this is the thermal conductivity for the electronics with respect to temperature. Also, you can see this is the thermal conductivity for the phononic. And here you can see this is the jetting, that is basically for the figure of merit. So thermoelectric property you can also study from this jet input file. So before calculating this jet input file, first we need to calculate this Hessian input file, so that it will take the Hessian matrix, that is dynamical matrix, from their output file. So if you want to design a device structure, so first you need to import some material to decide their electrode. Like here you can see I would like to import some gold material. So any material you can select, like this is the import option, import local. This is the 3D material, conductor, pure metals. Here you can see this is the gold. So if you want to select this golds, you can select this open, then this material will be imported. So this is our simple gold structure. If you want to show the FCC, like face center cubic structure or body center cubic structure, then you can select this build option, select this redefine crystal. Here you can see this is the face center cubic structure and this is the body center cubic structure. So I would like to select this face center, select this preview, and you can see this is the face center cubic structure of the simple gold structure. Also, you can see this is the body center cubic structure of the gold material. So in this structure, I would like to select this FCC, select this preview, select this build option. And if you want to create a supercell, select this build option, select this redefine crystal. So as per your need, you can increase the number of atom. Like you can see 2 times in the A direction, 2 times in the B direction, and 4 times in the C direction. Select this preview. You can see this is the supercell of this gold material. And then you can select this build option. So desired structure you can create from this builder. So you can see this is the 3D viewer where you can see XY view, YZ view, YZ view, YX view, and ZX view. Suppose if you want to show the XY view of this supercell gold material, you can see. And if you want to delete any atom from this supercell, you need to draw the rectangle, select the atoms, select this delete option. Now you can see the atom has been deleted. Again, if you want to delete some more atom, you can select this delete atom. So this is our supercell structure of the gold material in XY direction. You want to select this ZX view, You can see. So if you want to delete some more atom, so you can see I would like to delete these atoms and deselect these atoms. Select this delete option. So this is my desired left electrode. If you want to define the same right electrode, you need to select this material, go to this mirror atom. You can see this is the mirror atom. You need to define the normal vector xyz position. You can define the distance between the electrode. Then you can enable this copy option, so that the same structure you can show on the right side. You can see I would like to select this XY view. I would like to define 5 angstrom distance between the electrode. You can enable this copy option. Then you can select this apply. You can see this is my left electrode. This is my right electrode. So if you want to show all the atoms inside the same unit cell, so then we need to increase the vacuum energy. So whenever you increase the vacuum energy from this structure, then all the atom will be in the same unit cell. So that you need to select this convert to crystal. Here you can see this is the vacuum energy in the A direction, vacuum energy in the B direction, and this is the vacuum energy in the C direction. So here I would like to increase the vacuum energy 36 angstrom, and then now you can see all the atom inside the same unit cell. Similarly, if you want to increase the vacuum energy from the V direction, you can enter the value, like you can see 20 angstrom in the B direction. Also, I would like to increase 20 angstrom in the A direction. So once you increase the vacuum energy, you can select this build option. So if you want to show this structure into center position, here you can see we have the center option, like center along A, center along B, and center along C. So in any direction you can select, like you can see this is the center along B. And suppose if you want to include some molecule in the center region, like here you can see, like if you want to include some molecule in the center region, either you can create a molecule from this molecule builder, or you can import the molecule from our existing database. So you can see I have already created the benzene molecule. Like you can see this is my benzene molecule. So the same benzene molecule you can also create from this molecule 2D builder. So if you want to add this benzene molecule in this structure, so you need to select the molecule, Control C, that it will be copy, and here you can paste. So you can select this structure and you can Control V. You can see this is our benzene molecule. If you want to move this benzene molecule in center position, you need to select this center option. You can also rotate this molecule in the same direction. So we need to select this rotation. Here you can define the angle. Then you can choose the direction. Like you can see, this is the counterclockwise y-axis. Again, I would like to define 45 and in the z direction. So if you want to add any other atom in between these two atoms, you can see this is the add new atom option. So if you want to add, you need to select the atom and then select this add new atom. You can see the new atom has been added. Similarly, you can select this to select this add new atom. So you can see this is the default gold that has been selected. So if you want to change this gold and this gold with another atoms, here you can see this is the replace atom. So we can replace this gold with any other element. Like you can see, this is the phosphorus. I would like to select. Again, I would like to select this gold and replace with the phosphorus. And to make a connection, we need to click on this recalculate linker bond so that all the atom will be connected by the covalent bond. Here you can see, I would like to select this recalculate linker bond, and now the atom has been connected. So this is my desired structure that I wanted to create. Now you can convert this structure into device. So if you want to convert this structure, here you can see this is the convert to device option. So in the device structure, you can see we have the left electrode, right electrode, bottom electrode, top electrode, front electrode, and back electrode. So up to 6 probe device structure you can easily simulate. So as per your device, you need to select the electrode. Here you can see only 2 electrode is possible, left electrode and right electrode, because there is no atom at the top and bottom. So we can select left electrode, right electrode, select this preview. You can see this is our left electrode and this is our right electrode. If you want to increase the value of electrode, so here you can enter the value like -6 angstrom the left electrode and 6 angstrom at the right electrode. You can select this preview. Now you can see the value of electrode has been increased. So in that way, you can convert any structure into device. Then you can select this build option. So this is my two probe molecular based device structure, where we have the left electrode, gold material. Also, we have the right electrode, gold material. If you want to change any electrode with any other atoms, you need to select this replace atom. Like if you want to create a aluminum right electrode, you need to select this aluminum, select this OK. You can see these are the different electrode material, right electrode and left electrode. And this is our center region. Here you can see undo redo option are there. So this is our two probe molecular based device structure. If you want to simulate this device structure, here you can see simulator, NanoDCAL, and here you can see we need to define the DFT plus NEGF parameter. And if you want to convert this structure into transistor, like if you want to define some gate, source, drain, then you need to select this transistor. So first I would like to define some DFT plus NEGF parameter for this two probe. You can see these are the basic settings, contour integral, and this is the electrode. Here we need to define the electron temperature, electrode voltage, and K point for the left electrode, and the similar value for the right electrode. So any value you can define as per your need. Like suppose if you want to define some 0.5 volt at the left electrode, and if you want to define minus 0.5 at the right electrode, then you can enter the value. So any value you can define as per your need. Then you can move on this iteration control, basic set. Here you can see this is the doping option. So if you want to include the doping, so first you can generate the VCA input file. You can see if you want to generate, so this VCA.input file and this doping value you can generate, then you can apply for the device structure. Here you can see it will take, I have already generated the doping. Also you can change the atom element. And this is for the spintronics application. So once you define the parameter, you can generate the input file. Then it will generate 3 input file. Like you can see, it has generated the SCF.input file of the device, the SCF.input file of the left electrode, and the SCF.input file of the right electrode. If you want to show the script for this left electrode, here you can see we have total number of atom 14. This is the right electrode. And here you can see this is the device. Left electrode and right electrode, and also you can see this is the voltage value. So before calculating the SCF.input file of the device, first we need to run the SCF.input file of the left electrode and right electrode, then you can go for the device. Because this SCF.input file will take the output from the left electrode and right electrode. You can see it will take the output from the left electrode and right electrode. And if we talk about the analysis properties for this device structure, so we can select simulator, NanoDCAL, and here you can see this is the analysis. So these are the device property that you can study, like density of state, effective potential, total energy, scattering state, transmission spectrum, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, and Seebeck coefficient. So any parameter as per your need you can select. Like you can see density of state, effective potential, total energy, scattering state, transmission, photocurrent, IV curve. So if we talk about this photocurrent, you can see we need to define the photocurrent polarization basis E1 and E2. Also we need to define the polarization vector like linear polarization, left circular polarization, right circular polarization, elliptical polarization, oblique elliptical polarization. So these are the various polarization vector, and then you can define the phi and theta. So there is minimum value, maximum energy, maximum value, and interval you can also define. Then you can move on this photon energy range, minimum, maximum energy, and delta you can define, K point sampling, and then you can irradiate your atom. So if you want to irradiate your atoms, like if you want to fall the light on the center part, so center part atom you can select this select option, then their atomic indices will be selected. So in that region, the light will be fall. And once you select this OK, then you can calculate the photocurrent. And this is for the IV curve. You can see this is the Seebeck coefficient. You can define the energy range, temperature range. So the device simulation will take some time to simulate this structure, because in this device we have 70 atoms. So if you want to convert this structure into transistor, so we have the simulator, NanoDCAL, select this transistor. You can see this is the gate parameter. You can define the spatial region, dielectric permittivity, and the oxide thickness. If you want to enter the value of oxide thickness, you can see this is the oxide thickness. You can see this is the gate voltage. So as per your need, you can define the gate voltage. You can select the gate type, top and bottom. Here you can see this is our gate, this is our source, and this is our drain. You can also vary the gate region. You can see. Also, you can decide the source. You can see source is at the right side. If you want to change at the left side, so this is our source, drain, and this is the gate terminal. You can also define the biasing voltage. Any biasing voltage you can define as per your need. Define the basic set, define the IV curve, K point sampling, basic setting, contour integral. You can define the electrode parameter, iteration control, basis set, spintronics application. Then you can click on this generate file, so that it will generate the input file for this transistor. Then you can analyze their IDVD characteristics and IGVG characteristics. You can see I would like to generate the file. Now you can see drain voltage is 0, gate voltage is 0, drain voltage is 1.2, gate voltage is 0.5. So the input file of the SCF and IVC input file has been generated. So once you simulate this structure, this input file, then you can analyze from this transistor plot. So if I show some existing file that I have simulated earlier, because this device will take more time to simulate this structure. So I can open my existing project. You can see multiple project I have simulated. You can see this is the bifinal device structure that I have simulated. So you can see this is the bifinal device. So if I import another project, you can see same device structure I have simulated. And I have simulated the transmission spectrum, density of state, Coulomb potential, and total electron density. I have also simulated the IV curve for another project. So if you want to show this density of state, here you can see in the projection, I have selected the atom. So this is our density of state with atom wise. Also, you can see this is the Coulomb potential. You can see this is the Coulomb potential 3D view. This is the 2D view along x-axis, y-axis, and z-axis. This is the planar display. This is the stereoscopic display along z-axis, y-axis, and x-axis. And you can see this is the 1D view along xy plane, yz plane, and xz plane. So if we talk about the IV curve and photocurrent, you can see I have simulated this IV curve. So at various biasing voltage, I have simulated like 0.6, 0.8, 1.0. And this IV curve input output file, you can open in the MATLAB. So you can import this file into MATLAB. And you can see multiple output file like this is the transmission spectrum for the spin up, spin down. This is the spin up and spin down both. And this is the total transmission spectrum. Also, you can see this is the Seebeck coefficient with respect to temperature. This is the spin up. Red one is for the spin down. So this is the Seebeck coefficient. And if you want to show Seebeck spin and charge coefficient, you need to select and you can see. This is the with respect to chemical potential energy. And if we talk about the transistor properties, so I can show. So you can see this is the silicon based device structure and I have simulated the result. So the IDVD characteristics I have simulated, you can see. And for the transistor plot, you need to select the simulator, NanoDCAL, select this transistor plot. You need to select your project. And you can see this is my transistor. So this file you can select this select folder. And here you can see this is the IDVD characteristics at different gate. like 0.1, 0.2, and 0.3. So whenever you define the accurate parameter, then you can get the accurate result. So this is the IDVD characteristics, and here you can see this is the IGVG characteristics. Here you can see this is my MATLAB. So I can import my file. You can see this is the device that I have simulated at 0.4 biasing voltage. Here you can see this is the current voltage curve.mat file. So you can double click on this mat file, and here you can type command data and then press the enter. Now you can see in this structure also we have defined the spintronics application so that we can get V1, I1, and here you can see this is the V2 0.4 and this is the I2 1.7970 into 10 to the power minus 5. So this data, simulated data you can take and then you can go to the new script. So if you want to plot the final graph, you can take the data, go to the new script. Here you can see I have already written. So you can see this is my voltage V1. This is my current voltage V2. This is the I1 total current. This is the I1 spin current or the spin up. This is the I1 spin down current. This is the I2 total current. This is the I1 spin up current. And this is the I2 spin down current. And here you can see I have written this command to plot the graph. You can see also I have defined at the x-axis I have defined the voltage, y-axis I have defined the current. So once you write this script, select this run option, then it will plot your graph. You can see this is the spin current plot because we have defined the collinear spin. You can see this is the I2 total current, I2 spin up current. This is the I1, I2 spin down current. This is the I1 spin down, spin up, and I1 total current. These are the current, and here you can see I have defined the voltage from 0 to 1. So IV curve is also possible. And if we talk about the photo current, you can see this is my device. And here you can see I have simulated the photo current. You can see for the lead first and second. If we talk about any other project that I have simulated, You can see this is the bilayer CuPC molecule structure. You can see the same structure I have simulated. This is our molecule, CuPC molecule, and this is our graphene. Here you can see I have simulated transmission spectrum, total electron density, Seebeck coefficient, and effective potential. So I have shown you maximum properties of this software from this NanoDCAL. So if you have any specific query, so you can ask.
Excuse me, sir.
Yes, sir.
Can you show the how one metal surface and hydrogen heterojunction?
Metal surface and hydrogen heterojunction.
Only hydrogen.
Okay, nice.
Maybe we can take copper oxide, and it's any one surface or any HCl plane.
Okay. So first I would like to select this hydrogen.
Can we take only one hydrogen? Because if we take the many hydrogen atom, they take long time.
Okay, so you want only one
hydrogen atom and any HCl plane of the metal oxide.
So you can see this is the hydrogen.
Okay.
And if you want to import some metal oxide.
And it's any plane, for example, 110 plane.
So any more metal oxide you can import.
Copper oxide, copper.
So you can see this is the copper oxide. And you can copy this structure, Control C, and you can select this structure. And in this structure you can paste. And you can choose the location of this structure. So you can also move at any position.
We can optimize this structure.
Yes, we can optimize.
Okay.
So once you design the structure, for optimization you can select simulator, NanoDCAL, select this relax option. Here you can select the method, either MD or CG, and you can generate their input file.
And we can calculate the energy from the
Yes.
Okay.
Yes. So once you run this input file, then it will generate a optimized structure, and that optimized structure you can import, like that I have imported this one. And then you can simulate their properties. So first you can define the SCF parameter, then you can go to the analysis.
Okay, thank you, sir. Thank you, thank you.
Okay, sir. Thank you.
Sir, we can discuss today for Gibbs free energy.
Yes, sir. Every energy you can calculate from this total energy. From this total energy you can calculate. So for this total energy, we need to write some command. Here you can see. So this command we need to write so that we can calculate the total energy. And in that total energy, we can get multiple energy, like Gibbs energy, kinetic energy, Vernal energy, VNA energy. So multiple energy we can get.
Only. Sir, if we have the time, 12 minutes, we can run for one program for energy.
So then take your time. Also we need to write some command. Here you can see. So whenever you select any structure, here you can see there are no parameter. So we need to generate and then we need to write the command. Here you can see the total energy input file has been, yes, generated. And here we need to write some commands. So I will show you command some so that you can plot.
Okay.
So could you please repeat analyzing plot?
Which analyzing plot, ma'am?
So for anything, like I'm facing a problem. So
Okay, no, so like first you can generate the device input file, SF.input file, left electrode input file, and right electrode input file. So once the file generated, then you can go simulator, NanoDCAL, select this analysis, and you can select any parameter, like you can see the density of state, and you can generate their input file. Once the left electrode input file, right electrode input file will be completed, then you can run the SF.input file of the device. Then you can run the density of state.input file.
okay, sir. So I'm asking about the plotting.
Like once the simulation completed, Here you can see. Like you can see, once the simulation completed, then it will generate an output file. You can see this is the density of state. So if you want to plot, you can right click, select this show view.
Okay, fine. So for everything, we don't need MATLAB, right?
No, only for IV calculation and some thermoelectric and photocurrent, you need MATLAB.
Okay, got it. Fine, sir. Thank you.
Like if you want to create some alloy structure, here you can see. For the alloy, you need some information like the structure, the previous lattice parameter, ABC value, and the element and their fractional coordinate point P1, P2, and P3. Then you can create an alloy structure. So in the second session, I will show you the commands so that you can plot the total energy.
Okay, sir. Thank you. Sir, I have executed the program for charge, but the message is showing that we cannot support this type current.
Yes, sir. So charge analysis will also open in the MATLAB. Here you can
Okay,
see.
okay, right.
So charge will open in the MATLAB. So that file you can import.
Okay, sir. Thank you. Thank you.
So from my side, thank you so much to all of you. So we will meet you at 2 p.m.
Sir,
so that you can do
I
the,
have one
yes.
question.
Yes, sir.
You provide the software. How many days we can use that one? Because we need some practice.
Sir, I am working at this software from last 2 years.
Okay, we can use the your provided software for practice. Okay.
Yes, sir.
Okay, sir. Thank you.
So I can help you in the simulation part, and the theory part you need to study. So once again, thank you so much to all of you.